Right. Hello everyone, welcome to our presentation. As you can see on the screen, our topic is three-phase bridge rectifier with R and RL load. Next, today's presentation is divided into 7 of us, where I am going to give a brief introduction about a three-phase bridge rectifier and a numerical. Sejal will tell us applications of three-phase bridge rectifier, and Grishma is going to explain the waveforms and characteristics. And Tanushri will tell us types of bridge rectifier. Pranav is going to explain working principle, and Uddesh will tell us the advantages and disadvantages of three-phase bridge rectifier. And Payal will explain the equation of three-phase bridge rectifier. Next. This presentation is structured as follows. So first there is introduction, working and circuit diagram, waveform of three-phase bridge rectifier, equation, types of bridge rectifier characteristics, bridge rectifier IC, advantages and disadvantages of bridge rectifier, applications, and a numerical. Next. So let's see the history of bridge rectifier. The diode circuit was invented by Polish electrotechnician Karol Polak and patented in December 1895 in Great Britain and in January 1896 in Germany. In 1897, the German physicist Georg independently invented and published a similar circuit. Today, the circuit is sometimes referred to as a Great's circuit or Great's bridge. Prior to the availability of integrated circuits, a bridge rectifier was constructed from discrete components, that is, separated diode. Since about 1950, a single four-terminal component containing the four diodes connected in a bridge configuration become a standard commercial component and is now available with various voltage and current ratings. Next. So introduction. First of all, I did like to give an overview of three-phase bridge rectifier, and next I will focus on types in which bridge rectifier are classified. So let's start. A bridge rectifier circuit is a common part of electronic power supplies. It is an AC to DC converter which rectifies main AC input to DC output. Many electronic circuits require rectified DC power supply for powering the various electronic basic components from available AC main supply. We can find this rectifier in a wide variety of electronic AC power devices. Like it is commonly used for high power applications because they have the highest possible transformer utilization factor for a three-phase system. Bridge rectifier can be constructed with four or more diodes or any other control solid state switches. Depending on the load current requirements, a proper bridge rectifier is selected. Bridge rectifiers are classified into several types based on the following factors like types of supply, controlling capability, bridge circuits configuration, etc. Bridge rectifier are mainly classified into single and three-phase rectifier. Both these types are further classified into uncontrolled, half-controlled, and full-controlled rectifier. Also, the working and circuit diagram will be explained by Pranav.
Working and circuit diagram. In power circuit diagram for a three-phase bridge rectifier using 6 diodes as shown in figure. The diodes are arranged in 3 legs. Each leg has 2 series connected diodes. Upper diodes D1, D3, D5 constitute the positive group of diodes. The lower diode D2, D4, D6 from the negative group of diodes. The three-phase transformer feeding the bridge is connected in delta star. This rectifier is also called as three-phase six-pulse diode rectifier, three-phase full-wave diode rectifier, or three-phase D6 diode rectifiers. Positive group of diode conduct when these have the most positive anode. Similarly, negative group of diode should conduct if they have the most negative anode. In other words, diode D1, D3, D5 forming positive group would conduct when this experiences the highest positive voltage. Likewise, diode D2, D4, D6 will conduct when these are subjected to the most negative voltage. Next slide explained by Grishma.
The three-phase bridge rectifier waveform starts from the Vs, from the source voltage waveform VA, from figure A, that from omega t is equals to 30 degree to 150 degree, 150 degree voltage VA is more positive than the voltage VB and VC. Therefore, diode D1 conducts connected to line A conducts during the interval at omega t is equals to 30 degree to 150 degree. Likewise from omega t is equals to 150 degree to 270 degree, voltage VB is more positive as compared to VA and VC. Therefore, diode D3 connected to line B conducts during this interval. Similarly, diode D5 from the positive group conducts from omega t is equals to 270 degree to 390 degree and so on. Also that from omega t is equals to 0 degree to 30 degree, VC is the most positive Vc is the most positive. Therefore, diode D5 from the positive group conducts for this interval. Conduction of positive group diodes as shown in figure B as D5, D1, D3, D5, etc. Voltage VC is the most negative from omega t is equals to 90 degree to 210 degree. Therefore, negative group diode D2 connected to line C conducts during this interval. Similarly, diode D4 conducts from 210 degree to 330 degree and diode D6 from 330 degree to 450 degree and so on. Also that from omega t is equals to 0 degree to 90 degree, VB is the most negative. Therefore, diode D6 conducts during this interval. Conduction of negative group diode is also is shown as D6, D2, D4, D6, etc. as shown in figure B. During the interval at omega t is equals to 0 degree to 30 degree, it is seen from figure B that diode D5 and D6 conducts uh, as shown in previous figure that conduction of D5 connects load terminal P to line terminal C. Similarly, conduction of D6 connected load terminal Q to line terminal B. As a result, load voltage VPQ is equals to V naught is equals to line voltage VCB. First positive subscript corresponding to a C and second negative subscript corresponding to B from omega t is equals to 0 degree to omega t is equals to 30 degree. Likewise, during omega t is equals to 30 degree to 90 degree, diode D1 and D6 conduct. Conduction of diode D1 connect P to A and D6 to B. Therefore, load voltage during this interval is V naught is equals to line voltage VAB. Similarly, from interval 90 degree to 150 degree, diodes D1 and D2 conducts and V naught is equals to line voltage VAC. From this interval 150 degree to 210 degree, diodes D3 and D2 conduct and V naught is equals to line voltage VBC and so on. Output or load voltage waveform is drawn by a thick curve as shown in figure C. Next slide will explain by Payal.
Equation of a three-phase bridge rectifier. Average value of load voltage is given by V0 is equals to 1 upon periodicity A1 to A2 VAB into d omega t. It is seen from figure 3.40 from the earlier slides that the value of VAB at omega t is equals to 0 is VML into sine 30 degree and its periodicity is a 60 degree or a pi by 3 radian. Therefore, V0 is equals to 3 by pi integration from pi by 6 to pi by 2 VML sine omega t plus 30 degree into d omega t. Then we get 3 into VML upon pi is equals to 3 under root 2 V1 upon pi is equals to 3 into under root of 6 Vp upon pi, where VML is equals to maximum value of line voltage, V1 is equals to RMS value of line voltage, and Vp is equals to RMS value of phase voltage. Average value of output voltage V0 can also be obtained as under: take any sinusoidal wave and integrate it from 60 degree to 120 degree. It is because the voltage pulse area required extended from omega t is equals to 60 degree to omega t is equals to 120 degree. For the sine omega t functions, that is VA is equals to 3 by pi integration from pi by 3 to 2 pi by 3 VML into sine omega t d omega t is equals to 3 VML upon pi. For a cosine function, cos omega t voltage a pulse of a 60 degree, duration extended 30 degree to the left of its peak and 30 degree to the right of the peak. Therefore, V0 is equals to 3 by pi integration from pi by minus pi by 6 to pi by 6 VML cos omega t d omega t is equals to 3 VML upon pi. RMS value of output voltage is given V naught R is equals to 3 by pi integration from pi by 3 to 2 pi by 3 VML square sine omega t d omega t whole bracket square 1 by 2 3 VML square upon 2 pi into omega t minus sine 2 omega t upon 2 limit pi by 3 to 2 pi by 3 whole bracket 1 by 2 square is equals to 0.9558 VML. Next slide. Next slide. Ripple voltage is given. VR is equals to under root of V square V naught R square is equals to V naught square is equals to 0.9558 square minus 3 upon pi by square whole bracket square 1 by 2. Voltage ripple factors is given. VRF is equals to VR upon V0 is equals to 0.0408 upon 3 by pi is equals to 0.0427 or 4.27%. FF is equals to V0R upon V0 0.9558 VML upon 3 by VML is equals to 1.009. RMS value of output current I0 R is equals to V0 R upon R is equals to 0.9558 upon R VML is equals to 0.9558 IML. PDC is equals to V0 upon I0 is equals to 3 by pi square VML into IML. PAC is equals to V0 R into V0 R is equals to 0.9558 VML into IML. Rectifier efficiency 3 pi by square into 1 upon 0.9558 is equals to 0.998 or 99.82%. For a resistive load, peak current through the each diode is IML is equals to VML is equals to under root of 3 VMP upon R. It is seen that from the waveform of the line current IA or transformer secondary current IS, that I periodicity of this current is a pi rad, and this current has a two pulse each of 60-degree duration for each periodicity of pi rad. Therefore, RMS value of line current is equals to RMS value of transformer secondary current. IS is equals to 2 pi integration from pi by 3 to 2 pi by 3 I square ml sine square omega t into d omega t in a whole bracket 1 by 2 square is equals to 0.7804 IML. Transformer VA rating is equals to 3 VS into IS is equals to 3 into VML upon under root 6 into 0.7804 IML. TUF is equals to PDC upon VA rating of transformer is equals to 3 by pi square into under root of 6 upon 3 into 0.7804 is equals to 0.9541. It is seen from diode current waveform of figure number 3.40D that average value of diode current is ID is equals to 2 upon 2 pi integration from pi by 3 to 2 pi by 3 IML into sine omega t d omega t is equals to IML upon pi. Then RMS value of diode current IDR is equals to 2 upon 2 pi integration from pi by 3 to 2 pi by 3 IML square sine square omega t into d omega t. Then whole bracket square 1 by 2 is equals to 0.582 IML. The next slide will be explained by Tanushree.
Coming to types of bridge rectifiers. Bridge rectifiers are classified into several types based on these factors, such as type of supply, controlling capability, bridge circuit configurations, etc. Bridge rectifiers are mainly classified into single and three-phase rectifiers. Both these types are further classified into uncontrolled, half-controlled, and full-controlled rectifiers. Some of these types of rectifiers are described below. Next. First, we will see single-phase and three-phase rectifiers. The nature of the supply, that is single phase or three phase supply, decides these rectifiers. The single phase bridge rectifier consists of 4 diodes for converting AC into DC, whereas a three phase rectifier uses 6 diodes as shown in the figure. These can be again uncontrolled or controlled rectifiers depending on the circuit components such as diodes, thyristors, and so on. Next. Now we will see uncontrolled bridge rectifiers. This bridge rectifier uses diodes for rectifying the input as shown in the figure. Since the diode is a unidirectional device that allows the current flow in one direction only, with this configuration of diodes in the rectifier, it doesn't allow the power to vary depending on the load requirement. So this type of rectifier is used in constant or fixed power supplies. Next. Controlled bridge rectifier. In this type of rectifier, AC or DC converter, or we can say rectifier, instead of uncontrolled diodes, controlled solid state devices like SCRs, MOSFETs, IGBTs, etc. are used to vary the output power at different voltages. By triggering these devices at various instants, the output power at the load is appropriately changed. Next slide will be explained by Grishma.
Now, let's see a characteristics of bridge rectifier. Uh, the characteristic of bridge rectifier includes three types. First one is a repel factor. Second is a peak inverse voltage, that is PIV, and third one is efficiency. Next. In repel factor, the smoothness of the output DC voltage is measured by the factor is called as repel factor. The ratio of repel voltage to pure DC voltage is called repel factor in mathematical term, which is given by gamma is equals to under root Vrms square by Vdc minus 1. For bridge rectifier, the repel factor is 0.48. Next. Now, in peak inverse voltage, that is PIV, uh, the peak inverse voltage is defined as the maximum voltage that a diode can withstand in a reverse bias condition. During positive half cycle, the diode D1 and D3 are in the conducting state, while D2 and D4 are, are in the non-conducting state. Similarly, during the negative half cycle, diode D2 and D4 are in the conducting state, and diodes D1 and D3 are in the non-conducting state. Next. The third one is efficiency. The rectifier efficiency is defined as the ratio of DC output power to the AC input power. The maximum efficiency of bridge rectifier is 81.2%. This is how rectifier efficiency determine how efficiently the rectifier convert AC into DC. Uh, Now next slide will explain by Tanushree.
Now we will see bridge rectifier IC. The bridge rectifier like RB156 IC pin configuration is discussed below. Let's see pin 1, which we called as phase or line. This is an input. This is an AC input pin, where the connection of phase wire can be done from the AC supply towards this phase pin. Then pin 2, that is neutral pin. This is the AC input pin where the connection of the neutral wire can be done from the AC supply to this neutral pin. Then pin 3, which is positive pin. This is the DC output pin where the positive DC voltage of the rectifier is obtained from this positive pin. Next, pin 4 is negative or ground. This is the output pin where the ground voltage of the rectifier is obtained from this negative pin. Next slide will be explained by Sejal.
Rectification. The rectification of RB1 is bit rectifier. One is output DC current is 1.5 ampere. Second one is the maximum peak level voltage is 800 volt. Third one is output voltage is equal to U into VRMS minus U volt. The maximum input voltage is 50 volt. Voltage drop for each B is 1 volt to 1 ampere. The earth current is 50 ampere. The highest DC current of this rectifier is 1.5 ampere. The next type will be wounded.
Then advantage of three-phase bridge rectifier. Then first advantage of bridge rectifier is the efficiency of the bridge rectifier is higher than the efficiency of the half-wave rectifier. However, the rectifier efficiency of the bridge rectifier and the center tapped full wave rectifier is the same. The second advantage is the DC output signal of the bridge rectifier is smooth than the output DC signal of the half-wave rectifier. Then last advantage is in a half-wave rectifier, only half of the input AC signal then is used and the other half wave is blocked. Then half of the input signal is wasted in the half-wave rectifier. However, a signal bridge rectifier to electric current is allowed during the positive and negative half cycle of the input AC signal. Then of the output DC signal is almost equal to the input of AC signal. Then next slide. Then next slide is disadvantage of three-phase bridge rectifier. Then first advantage is the circuit of the bridge rectifier is complex when compared to half-wave rectifier and the center tapped full-wave rectifier. Then bridge rectifier use 4 diodes while half-wave rectifier and center tapped full-wave rectifier is use only 2 diodes. Then second disadvantage is when a more diodes are used, more power losses occur in a center tapped full-wave rectifier. Only one diode conduct during each half cycle, but the bridge rectifier 2 diodes connect in series conduct during each half cycle. Hence, the voltage drop is higher in a bridge rectifier. Then next slide will be explained, Sejal.
Application of bit rectifier. Bit rectifiers are commonly used for high power applications because they have highest possible transformer utilization factor. They are used for electrochemical voltage like motion diode and control power supply. It is used in a voltage multiplier and modulation. It is also used for mobile phone and radio. Next, I explain by Uvada.
So let's see a small example with the help of numerical. The four diodes used in a bridge rectifier circuit have forward resistances which may be considered constant at 1 and infinite reverse resistance. The alternating supply voltage is 240 volt Vrms and load resistance is 480 RMS. So in this we have to calculate first mean load current and second power dissipated in each diode. So firstly we have to calculate maximum AC voltage Vm. To calculate maximum AC voltage, uh, Vm is equal to Vrms into root 2 into V, where Vrms equal to 240 volt. So at any instant in the bridge rectifier, two diodes in series are conducting. Therefore, total circuit resistance is 2 Rf plus RL. where RF is equal to forward resistance and RL is equal to load resistance. Maximum load current IM is equal to VM by 2RF plus RL. VM is equal to maximum AC voltage. So by substituting this value, 240 into root 2 by 2 into 1 plus 480, we get 0.7 ampere. Then for calculating mean load current, IDC is equal to 2 Im by pi, where Im is equal to maximum load current, and by substituting the value 2 into 0.7 by pi, we get 0.45 ampere. Then second, we have to calculate power dissipated in each diode. Since each diode conducts only half a cycle, diode RMS current is IRMS is equal to Im by 2. The value of Im is equal to 0.7 by 2. So we get 0.35 ampere. Power dissipated in each diode is equal to IRMS square into RF is equal to 0.35 square into 1. We get 0.123 watt. Next. Thank you.